Right. So we are going to talk about solutions today. Now, a solution can either be concentrated. If it's concentrated, it's really strong. Think of having the Kool-Aid mix that has too much Kool-Aid powder in it. It needs to be watered down. A dilute solution is a weak solution. It doesn't have enough Kool-Aid powder in it. You could barely taste it. It tastes watery. Now, a solution has two parts. One, you have the solute. That's what's being dissolved. So if we have Kool-Aid, the powder here is the solute. That's what is being dissolved. The second one, the second part of a solution is the solvent. Often that's water because it's what is doing the dissolving. Now, an unsaturated solution is one that has less amount of solute dissolved than the maximum that could be dissolved in solution. A saturated solution holds the maximum amount of solute per amount of the solution. You can't add any more solute to the solution and expect it to dissolve in a saturated solution. The powder is just going to fall down to the bottom of the glass or the pitcher and it won't dissolve at all. There is a maximum amount that each solution can hold. For example, if we're making salt water, you can only put 36 grams of salt into 100 grams of water. That's a saturated solution. The salt will, if you add more, it'll just fall to the bottom because it can't hold anymore. A supersaturated solution contains more solute than the usual maximum amount, and they're unstable. Fudge actually forms from a supersaturated solution. You have your milk, you have a bunch of sugar, and you're stirring it as you bring the temperature up. Raising the temperature actually increases solubility, so you're able to dissolve more than you normally would. As it cools, if it sits and is undisturbed, it's not going to fall out of solution. Once you disturb it, it'll start falling out of solution. So the old-fashioned fudge, you have to beat it whenever it's cooled enough and beat until it loses its gloss. That's one of our holiday treats that my family loves. We make my grandmother's fudge, caramel and chocolate fudge. We used to make peanut butter fudge too, but then my son, we learned that he was allergic to nuts whenever he was a baby, and that was the end of that. I was sad, and my oldest was sad, but it was better to go without in that instance. Now, most solubility increases with increasing temperature. You increase the temperature, you can dissolve more things into the system. Now, the heat of solution is the heat taken in or released in a dissolving process. And usually that's an endothermic process. And when working with a solute that dissolves endothermically, the mixture will become cooler while you're dissolving. Baking soda and vinegar is an example of an endothermic solution. It doesn't drop drastically, but the temperature will drop a degree or two. Molarity is a way to measure concentration. It's the number of moles of solute per liter of solution. The volume is the total solution volume that results, not the volume of the solvent alone. So if I were to ask you how you would make a 0.15 molar solution of sodium chloride, well, we know that if we have a 0.15 molar solution, we have 0.15 moles of NaCl in 1 liter. If we just wanted to make 1 liter, it didn't specify, but 1 liter would be easy to make. We just wanted to make 1 liter. We'd multiply it by the amount that we want to make, which is 1 liter, and liters would cancel out, and we'd find that we have 0.15 moles of sodium chloride for every liter. But this isn't going to work because we don't go to a scale and measure out 0.15 moles. We need to calculate the molar mass. So we would look on the periodic table and we'd see sodium has a mass of 23.0. We have 1 sodium plus 1 chlorine, which has a mass of 35.45. And we add it up and we find the molar mass is 58.45 grams per mole. So now I can take my 0.15 moles of sodium chloride and change it into grams because we can go to a scale and calculate or weigh out the grams. My grams go on top because I need grams of sodium chloride. And my moles go on bottom because I need to cancel out my moles of sodium chloride. And it's 58.45 grams of sodium chloride per 1 mole. Let's do that. 0.15 times 58.45 gives us 8.77 grams of sodium chloride. So if we were to make 1 liter of a solution, we would need to weigh out 8.77 grams of sodium chloride. On this page, it's a little bit neater, and I walk you through the process. First, we determine the mass of sodium chloride to add to a 1.0 liter solution. If we're making 1 liter, we know that it has to contain 0.15 moles. Then we're going to use the molarity of the solution and the molar mass of sodium chloride to convert moles of sodium chloride to grams of sodium chloride. So here's the math shown more nicely than my writing is. And then we find that we have 0.15 moles of sodium chloride. We change it to grams using the molar mass found on the periodic table. We get 8.8 grams of sodium chloride. Now, we're going to do the same process here. How would you prepare 5.0 liters of a 1.5 molar solution of glucose, C6H12O6? So if we have a 1.5 molar solution, that means we have 1.5 moles of C6H12O6 for every 1 liter. But we don't want to make 1 liter like we did in the last question. We actually want to make 5 liters. So since we want to make 5 liters, we need to know how many moles we'll need. So we're going to multiply that by 5. So 1.5 moles of glucose divided by 1 times 5 gives us 7.5 moles of C6H12O6. Now that I have the number of moles of C6H12O6 of glucose, I can use that to learn how many grams, to calculate the number of grams. In order to go from grams or moles to grams, I need to use the molar mass from the periodic table. So I look at my glucose formula and I have 6 carbons times, if I look at the periodic table, mass of carbon is 12.01 plus I have 12 hydrogen. If I look on the periodic table from the mass, it's 1.01 plus I have 6 oxygen. If I look on the periodic table, that's 16. So 6 times 12.01 plus 12 times 1.01 plus 6 times 16 gives us 180.18 grams per mole is a molar mass of glucose. So now I take my 7.5 moles of glucose, C6H12O6. I multiply it, but what do I want to put? What do I want to find? I want to find grams of glucose. So what I want to find goes on top. My moles go on bottom. It's 180.18 grams. My moles of glucose cancel out. So 7.5 times 180.18 is 1350 grams of C6H12O6. There we go. That's how you would walk through finding the solution to the problem. So again, here you can see I've typed it out so it makes it look nicer. If you can't read my writing, we have our 5 liters times 1.5 moles per liter. That gives us our 7.5 moles of glucose. And then we change our moles of glucose using our molar mass, which I didn't show the calculation for, to our grams of glucose. Here is another problem. We add 32.0 grams of potassium chloride to a container, and then we add enough water to bring the total solution volume to 955 milliliters. So what is the molarity of this solution? Now here, we have to first look and see what we have. We have our mass is 32.0 grams of potassium chloride, and we have our volume of 955 milliliter. Okay, we know that molarity equals moles over liters. We don't have either one of those. So one easy thing we can do is change our milliliters into liters. We know there's 1 liter for every 1,000 milliliters, so our milliliters will cancel. And that gives us 0.955 liters. And in terms of the potassium chloride, we're going to have to use the periodic table to determine the molar mass. So we'll need to calculate how many moles we have of potassium chloride. If I look on the periodic table, I see that potassium, we only have 1 potassium, and it has a mass of 39.15. Plus, we have 1 chlorine, which has a mass of 35.45. We add those together, we get 74.6 grams per mole. Now we have our molar mass and we have our grams. We can calculate how many moles it is. So we take 32.0 grams KCl times, we want moles on top, because that's what we want to turn it into. And we put grams on the bottom, because that's what we want to cancel out. And it's 74.6 grams of potassium chloride. So now it's 32 times 1 divided by 74.6. And this gives us 0.429 moles of KCl. Now we have our moles and we have our liters. So we can now calculate our molarity. So molarity equals 0.429 divided by 0, our new volume, divided by 0.955 liters. This is moles. That's liters. So this gives us 0.449 molar solution of potassium chloride. Remember, if you have questions, let me know. We're just adding on to what we've learned in previous weeks. Okay, I want you to try these questions and then come back and push play and see if you got them correct. So for this one, what is the molarity of a solution that contains 2 moles of NaCl and 1 liter? We're looking for molarity. So our molarity, we know, is moles over liters. So this is 2.0 moles over 1 liter. So the molarity then would be 2.0 molar solution of sodium chloride. 2. How many moles of hydrochloric acid, HCl, are in 250 milliliters of a 0.50 molar solution? So our liters is 250 milliliters times 1 liter for every 1,000 milliliters. We have to convert it. So that's 0.250 liters. But we need to determine how many moles. We have our molarity. and that's 0.50 moles per liter. So we know molarity equals moles over liter. If we want to solve for moles, we multiply by liters on both sides. So the number of moles then, is equal to our liters times our molarity. And that is our 0.25 liters times our molarity of 0.5. Doesn't want to write here. Let's see if I can make it a little bit smaller. If that will write. So liters times molarity, which is our 0.250 liters times our 0.50 moles over liters. Our liters cancel. So that leaves us with 0.250 times 0.50. It gives us 0.125 moles, which is A. 3. What's the molarity of a solution? So we're looking for molarity. Made by dissolving 10.0 grams. This is mass of NaOH. And enough water to make 500 mils. So we have 500 milliliters. We know molarity equals moles over liters. We have grams and milliliters. The fastest is to change volume into liters by dividing by 1,000 milliliters. That gives us 0.500 liters. So now we have our liters. We just need to change our grams into moles. We have 1 sodium here. The mass of sodium is 23. If we look at the periodic table, we have 1 oxygen, whose mass is 16.00, plus 1 hydrogen, whose mass is 1.01. So if we add that up, the mass is 40.01 grams per mole for sodium hydroxide. So now that we have the molar mass, we can change our 10 grams into moles. We want moles, so that goes on top. Our mass goes on bottom because that's what we want to cancel out. This is moles of NaOH. Grams of NaOH cancel. So it's 10 times 1 divided by 40.01. That gives us 0.250 moles of NaOH, sodium hydroxide. Now, we want to find the molarity. Molarity is our moles, 0.250 moles, over our liters, which is 0.500 liters. If we plug that into the calculator, we get 0.500 molarity. which is C. If you have questions doing the math on this assignment, let me know. We're almost finished. Now, freezing point depression. Believe it or not, you use this you depend upon it pretty much every winter. Or if you make ice cream, you depend upon it. A solution always has a lower freezing point than the corresponding pure solvent. The amount the freezing point is depressed or lowered depends on the concentration. We see this happen when we put salt on the roads to melt the ice. The salt dissolves in the water and forms a solution with a lower freezing point than the water. Ionic solutes produce greater depression, freezing point depression, than covalents because it dissociates into ions. So if we had 1 mole of calcium chloride, it dissociates into 3 ions, Ca2 plus, Cl minus, and Cl minus. So it has 3 times the effect of 1 mole of sucrose, because sucrose doesn't affect or doesn't dissociate. So ionic compounds will always have a more greater effect on freezing point depression and on boiling point elevation. So the boiling point of a solution is greater than its pure solvent. So if we have water, for example, and you're bringing it to boil, that's a horrible thought. You have water, it's on the stove, and you're bringing it to boil. Then you have this water on the stove, but you put salt in it. Same amount of water, but this one has salt. This one is going to boil more slowly because it has a higher boiling point. It has a higher boiling point because you added salt to it. The salt doesn't make the water boil faster. That is a common misconception. The salt actually will actually salt the food already. And there are some claims that it makes the food cooks faster. I don't know if that's true or not, but adding salt to the water just adds salt to your food, and it takes it longer for it to boil. Now and that's just because there are more particles. There are more particles in the water. It's going to take more energy to get those particles moving and up to the boiling point. Now, the boiling point of a solution, no matter what, is greater than its pure solvent. You have the same effect with ions and covalent compounds. Ionic compounds will have a greater effect on boiling point because they dissociate. So remember, you have your calcium chloride. It breaks into 3 different particles. Your calcium ion, your chloride ion, and another chloride ion. And then you have your sugar, which is covalent. So calcium chloride will have 3 times the effect as 1 sugar molecule. Calcium chloride is rock salt. And if you're making ice cream the old-fashioned way, that's what you put on the outside in your ice to lower the freezing point, and it makes it colder. Now, solute particles affect the boiling point because they take up space at the surface where the liquid and gas meet, and it interferes with the ability of the solvent to escape. Because whenever again, you have your pot of boiling water here with the salt particles, your bubbles are forming down below, and they're going to rise and try to go and release, but these salt particles will block some of the bubbling. They get in the way of the ability of the solvent to escape, of those bubbles to be released. So think of it that way whenever you add salt to your water. Now, the higher the concentration, the greater the boiling point elevation. So if you have a 2 molar solution of calcium chloride and it's boiling in your pot, and then in another pot you have a 1 molar concentration of calcium chloride, it's the pot with the most effect would be the 2 molar calcium chloride solution. Antifreeze is a concentrated solution. You add it in your car, and your car, the moisture in your car, the water in your car isn't going to freeze. Now, one thing I do want you to realize is when you're sprinkling salt on the sidewalks in the wintertime to lower the freezing point of the ice so it becomes a liquid instead of remaining solid, yes, the more you add, the greater the freezing point depression, the lower the temperature has to go for the ice to melt. But salt dries up the soil, and you could kill the plants and some of the animals or organisms in the plants in the soil by putting too much salt on. So I once had a student ask me, "Hey, what happens if I just put a whole cup on it? Would I ever have to worry about having ice on my steps?" And I said, "Well, it depends on the temperature, but you would have the slipperiness, the graininess of the undissolved rock salt particles that you'd be walking on, which can be a slipping hazard as well. And if it's not dissolving and you're putting too much, then you're at risk of ruining the soil around you and killing your grass or your flower beds if they're near the sidewalk. So that is something to keep in mind. You have environmental effects of using salts as well. Now, solutions of gases in water. Whenever you drink soft drinks or carbonated beverage, this is actually a solution of carbon dioxide in the water. Now, the solubility of gas in a liquid depends on the pressure of the gas it's pushing down on the liquid. If you have higher pressure, solubility of the gas increases. So remember, like whenever you open up your can and you hear that, so here's your can of pop. You pop that top and you hear that sound like psh, that fizz sound that comes out. That's because it's no longer under that amount of pressure here. So the gas, because the pressure is no longer high, the gas can escape. And that's why over time, if you pour a can of pop into a glass and just walk away, over time, all of those gas particles get released and it tastes flat because it no longer has that carbon dioxide in it. The acidity is also much less because carbon dioxide in solution makes the water much more acidic because it turns into carbonic acid. Now, gas solubility decreases as temperature increases. So on hot days, if your pop isn't refrigerated, it will actually go flat faster. And I'll tell you this, once we went to the first time we ever flew, I was just shy of 14. And it was in August. And my dad had a Diet Coke or Diet Pepsi, I don't know. He drank either one, and he had left it in the car in the airport parking lot. And we didn't think anything of it, but when we came back, the top, instead of being all nice and flat, it was like bubbled over because the pressure increased as the temperature increased. Temperature increased, pressure increased. So remember, if the temperature increases, of Charles's law, if the temperature increases, the volume also increases proportionately. So we actually saw that, not in real time, but we saw the effects of increased temperature and increased volume by his can bubbling up. Now, gas, like I said, solubility decreases as temperature increases. So if you keep it cold, the gas solubility, you'll have the gas stay dissolved more so. So let's look at these practice questions. Which of the following would have the greatest effect on freezing point depression? Try to answer these on your own and then come back to see if you're correct. So we have 1 mole of glucose. This is covalent. 1 mole of sodium chloride. Well, this is ionic. So that means it's going to break down into 2 particles, sodium and chlorine. So it's going to have twice the effect as 1 mole of glucose because it has more particles. Then we have 1 mole of calcium chloride. Calcium chloride's ionic. It's going to break down into 3 particles. And then 0.5 moles of sodium chloride. We already know sodium chloride's ionic, and it's going to be 2 particles. Well, it has less concentration than either calcium chloride or sodium chloride, so it's automatically gone because concentration affects the boiling point and freezing point too. So now we're looking at whether it's going to be sodium chloride or calcium chloride. The more particles, they're the same concentration, so we just look at the particles. The more particles you have, the greater the effect. So the answer would be C, calcium chloride. For number 2, a solution is made by dissolving sodium chloride in water. Compared to pure water, the solution will have a higher freezing point and a lower boiling point, a lower freezing point and a higher boiling point, the same freezing point and boiling points, or a higher freezing point and boiling point. Well, we call it freezing point depression. So we know the freezing point, if it's being depressed, is going to decrease. And boiling point elevation, which means the boiling point is going to increase. So if we look, it's B, lower freezing point and higher boiling point. That's it for this week. I hope you have a wonderful day. Bye.